Problem B2, Appendix B, problem 2. Here we have this triangle with a mass of M, and it is a thin plate. Let's say the thickness is T. And we want to find the mass moment of inertia about x-axis and y-axis. The problem says radius of gyration. Radius of gyration, which we usually show it with k, or sometimes r, kx means radius of gyration about the x-axis, is nothing but a square root of ixx divided by m. So if we know what is the mass moment of inertia, you need to divide it to the mass, then root a square, then that's going to be radius of gyration. So the problem is asking what is the radius of gyration about the x-axis and y-axis, and because they have the similar process, I'm gonna just solve it for x-axis. But I'm gonna use 3 different methods to solve this problem, to explain you or to show you the different methods to approach this kind of problem. So let me start with the first one. Let's say this is the triangle, and this is x, y, this length is b, and this is h. And the total mass is m, as the problem stated. So if I want to start with the definition of the mass moment of inertia, let me write it here. I is equal to integral of r squared dm. If you want to start with the definition, we need to choose dm, or integral element. We need to choose an integral element somehow that we can cover the whole area with that different integral element. For 2D objects, and most of the times for 3D objects, probably the easiest one is choosing a cube with the size of dx and height of dy. And of course, the thickness of it is going to be t, the thickness of this plate. And I can cover the whole area with a very, very tiny cube like this, right? I can sweep the whole area to cover with this tiny integral element. And the distance of this element from, or the coordinate of this element, let's say it is x and y. So this distance is x, and this distance is y. So what's going to be the mass of it, because I need dm. dm, the mass of this tiny integral element, is going to be rho times the volume of it. And the volume is dx times dy times t, the thickness. So rho t dx dy is the mass of my element. Now, when I'm calculating ixx, let's write it here. R in this definition is the distance of my element from the x-axis, so this length, which is y. So the integral is going to be integral of y squared, so I replace r with y, times the mass, times dm, which is rho t dx dy. I can bring rho t out of this integral, and the integral is going to be, the remaining is going to be integral of y squared dx dy. But there is an issue here. We have dx dy, so my integral should be a double integral, right? Because I'm changing x in it, and also I'm changing y in it, which means if you wanna sweep the whole area to cover the whole mass, the x and y of this integral element is changing, right? So it means we have a double integral. So double integral of y squared dx dy. So which integral should be first? I mean, the integral over x should be first or over y? For this simple problem, it doesn't really matter. You can actually do x first and y first. But the problem is going to be, what are the boundaries of this integral? So when we are sweeping the whole area, x and y is changing. How the x is changing and how the y is changing. So if you want to do, or the way actually to define the boundaries and also which one you should do it first, let's say you are moving this around to cover the whole area. Your x is changing from this limit to this limit, right? We can say my x is changing from 0 to b, the x of this tiny piece, right? When we are moving it around, x is changing from 0 to b. And y is changing from y is equal to 0 to this line. Y of this guy is changing from 0 to here, right? These are the boundaries of my area. So x is going to change from 0 to b, and y is going to go from 0 to the equation of this line. And what is the equation of this line? It's quite simple. I'll leave it for you to find it, but it's going to be h minus h over b times x. Look at this equation. When x is equal to 0, y is going to be h, so it is correct. When x is equal to b, it's going to be h minus h over h times h over b times b, which is going to be 0. So it satisfies 2 points of this line, so it works. So this is going to be the equation of the line. Now, which one should come first and what are the boundaries of this integral? Look at these equations, these 4 lines. The one you have constant numbers in it is going to come second. So you need to do y integral first, then x integral second. So let me change this to y and x, which means you are doing y first, then x. The boundaries for y is going to be from 0 to h minus h over b times x. The second one is going to be over x, and x goes from 0 to b. So this is the way you choose boundary of the integrals. Can I do x first and y? Of course you can do. You can say my x is going from x is equal to 0 to this line, from this line to this line. Then your x, you can write the equation of this line in terms of y. X is going to be something in terms of y. You can easily find it. And y is going from 0 to h. If you write it that way, that's absolutely fine. You need to do the integral over x first and over y. Let's go with this one. The integral of y squared dy is going to be 1/3 of y cubed. So I'm going to have 1/3 of rho t from 0 to b. 1/3 of y cubed from 0 to this is going to be this guy cubed. So h minus h over b x cubed dx. Again, this is another simple integral. There are different ways to do this integral. Probably the simplest one is something which you call is u sub. So I can call all of this u and find dx in terms of du and change the boundaries. Then I can do this integral, right? So let's define u is equal to h minus h over b times x. Then du is going to be differentiation of h is 0. Differentiation of the rest of it is going to be negative h over b times dx. So ixx is going to be equal to 1/3 of rho times t integral. This is u, so u cubed. Dx from here is going to be negative b over h times du. So I can replace that with negative b over h times du. How about the boundaries? You need to change them too. X is equal to 0. X goes from 0 to b. Now we need to see how u is changing. When x is equal to 0, u is going to be equal to h from this equation. When x is equal to b, if you replace b here, if you substitute x with b, u is going to be equal to 0. Okay. Now we have a very simple integral. Negative b over h is constant. You can take it out of the integral. So I'm going to have negative 1/3 of rho t b over h times integral of u cubed is 1/4 of u to the 4. And from h to 0, it's going to be 0 to the 4 minus h to the 4, right? So at the end, I'm going to have negative 1 over 4 h to the 4. These negatives cancel out each other. So I'm going to have 1 over 12 rho b h to the 4 divided by h cubed. So this is the mass moment of inertia about x-axis. But as I told you before, we don't like it to write it in terms of rho. We need to have mass in it, m. I want to see the relationship between I and m. So I need to see what is m here. What is the mass here in terms of rho, t, and also b and h. Then separate the same thing here, replace it with m. So based on definition of density, mass is equal to rho times the volume. And the volume of this, this plate is going to be the area of this triangle times the thickness. Area of the triangle is 1 over 1/2 of b times h. So the total mass is going to be rho times 1/2 of bh times the thickness. This is the volume, right? So I need to separate the same thing from here and replace it with m. So if you separate this from here, the remaining is going to be 1 over 6, 1/2 of rho bht, which is the mass, and the remaining is going to be h squared. So I xx is equal to 1 over 6 mass times height cubed, squared. The radius of gyration, kx, is equal to square root of ixx over mass. So it's going to be 1/6 mh h squared over mass is going to be square root of h squared over 6, or h over square root of 6. This is the radius of gyration about the x-axis. And of course, you can do the same thing for y, and even without doing any math, because everything is symmetric about x and y. If you sweep, if you change the b and h, I about y-axis is going to be 1 over 6 times mass times b cubed. B squared, right? So this is the first method to find the mass moment of inertia about the x-axis. Let's do another method. So in the second method, for the same problem, I'm going to choose a different integral element. Again, let's say this is the triangle BH, and I want to find the mass moment of inertia about the x-axis. So instead of choosing a rectangular element for the integral element, I'm gonna choose this one, horizontal strips. If you choose tiny strips parallel to x with the distance of y from the x-axis, and let's say the height of it is dy. Now in the definition of integral, when we are saying I is equal to integral of r squared dm, if you choose this one as your dm, integral element, the mass of this strip, r, which means the distance of your element from the x-axis, is going to be y, because all the parts, all the points on this integral element, they have the same distance from x-axis. So r is going to be just y. So Ixx is going to be equal to integral of y squared times dm. But what is dm? What is the mass of this part? So the mass of this part, which is dm in the definition, is going to be equal to rho times the volume of this element. And the volume is going to be thickness, which is t, times height, which is dy, times this length. But what is this length? We need to find it. And I need to find it in terms of y, because everything is going to be in terms of y. So the equation of this line, if you remember from the previous solution, y is equal to h minus h over b times x. X, which is going to be the length of this, from this equation, you can actually find x in terms of y. You can change the order of this equation and write everything in terms of, find x in terms of y. That x is going to be the length of this, this element, right? So from this equation, x is equal to y minus b, h minus y times b over h, right? B over h times y minus, h minus y. Again, this is the equation of the same line, but I'm changing the order of things to write everything in terms of y, to find x in terms of y. And x, the meaning of x here, x is the points, x of the points on this line, means the height of this, or the length of this strip, right? So going back to the problem again, so Ixx is equal to integral of r squared, and r is the distance of the points on this element from the x-axis, which is y, times mass dm, and dm is equal to rho times t times dy times this length, which is going to be b over h times h minus y. So just replace dm here. So it's going to be rho t b over h times h minus y times dy. Now we have a simple integral again, and the integral is over y, and y goes from, when you are covering the whole area by sweeping this element, the y of the element goes from 0 to h. So the boundary of this integral is going to be from 0 to h. So let's write the remaining here. Ixx is going to be equal to, these are all constant numbers, I can take them out of the integral, rho t b over h times integral from 0 to h of y squared times this is going to be y squared times h minus y cubed dy, which is going to be equal to rho tb over h times integral of y squared is going to be 1/3 of y cubed, from 0 to h is going to be 1/3 of h cubed, times h, 1/3 of h to to the 4 minus integral of y cubed is going to be 1/4 of y to the 4 from 0 to h, 1/4 of h to the 4. And 1/3 minus 1/4 is going to be 1/12. So this is all together is going to be 1/12 h to the 4. And same as the previous one, we got the same thing, right? Then if you separate the mass from it, which we know the mass is equal to 1/2 of rho b t times h, and replace that with m, at the end we are going to have again 1/6 times mass times h squared. So this is the second way to solve this problem. So the difference between the previous one and this one, in the previous one we got we chose rectangular elements. Here we are choosing strips. The reason we are choosing these horizontal strips, because all the points on this strip, they have the same distance from x. So we know r is going to be equal to y of this strip. If I want to take integral over y-axis, then I need to choose vertical strips, because all the points on those vertical strips, they're going to have the same distance from the y-axis, which we are finding the mass moment of inertia about it. And the last method, third method, so this is method 2, method 3. Same problem, xy, and this is b, this is h. In the third method, I'm going to use these strips to find the mass moment of inertia about x-axis. In the previous one, I used horizontal strips. But I'm not going to start with the definition by choosing these elements, because if you start from the definition of the mass moment of inertia, which is this equation, then for your element, for your dm, the definition of r is the distance of your element from your axis, which is x here. What is the distance of this element from the x-axis? There is no answer for that, because different points of this element, they have different distances from the x-axis. The distance of this point is 0, the distance of this point is going to be something else, the distance of this point from the x-axis is going to be totally different number, right? So we are not going to be able to use this equation to find the mass moment of inertia of this about x-axis. But I can do a different thing. I can say this. I'm gonna call the mass moment of inertia of this tiny element about the x-axis di. Di xx is equal to, if you remember from the previous examples that I solved here, the mass moment of inertia of a rectangle, of a rod in general, about an axis which is passing through the end of it and perpendicular to the rod, is 1/3 of the mass times height squared, right? We can start with that. So the mass moment of this tiny strip, which is a rod, is going to be 1/3 the mass moment of inertia of it about the x-axis, 1/3 of the mass, which is dm, times height squared. And what is height? If I call this distance x, the height of the element from the equation of this line is going to be b over h, h minus h over b times x. This is the equation of this line, right? For any x, the height, the y of this point, which is on this line, is going to be this equation. So I can say the height, I can replace the height with that. H minus h over b times x squared. And where this comes from, again, comes from the previous example which I solved for you. We said whenever you have a rod with the mass of m and height of h, the mass moment of inertia about this axis is going to be 1/3 of mass times height squared. In the first example, we saw the mass moment of inertia of the same rod, which is about an axis which is passing through the center of it, is going to be 1/12 mass times height squared. So 1/3 of the mass times h squared, height is squared. So now this is the mass moment of inertia of this rod, but we have millions of these vertical rods to cover the whole area, to cover the whole mass, right? I need to add all of them together, which means I need to integrate this equation. Integral of di is I is equal to integral 1/3 of h minus h over b times x squared times dm. But what is dm? Can I write it in terms of x so I have everything in terms of x? Of course I can. dm is equal to rho times thickness of this plate times this area. And this area is dx, the width of this element, times the height of it, which is this. So it's going to be rho t h minus h over b times x times dx. So just replace dm in this integral with this. So it's going to be rho t is a constant number. I can take it out of the integral and put it here, times this value, same thing, so it's going to be cubed, times dx. And x goes from 0 to b, which is again similar to the previous integrals that we did. We can use u sub method and say this is u, then find dx in terms of du and do this integral, and then replace 1/2 of rho b ht with m. Then at the end you are going to get the same thing, 1/6 times mass times h squared.